Well, we've reached the point where we're going to start dealing with the math instructions. You will encounter these instructions whether you use them yourself or in troubleshooting. They're very simple. Add, subtract, multiply, and divide are the basic 4 math instructions. So we're going to start with add and subtract. One thing I do want to caution you about these instructions is that they execute every single scan that they're true. If your program scans 1,000 times a second, then 1,000 times a second, if the rung is true, it will add, subtract, multiply, or divide. So you have to be real careful what you're doing. In some cases, you may need a one-shot instruction if you only want it to add, subtract, multiply, or divide just once when the rung goes true. If you just have, if the rung's true, or if the conditions in the rung are true, then add, subtract, multiply, or divide, that's exactly what it's going to do with the sources every single program scan. So let's look at these instructions. Math instructions. Just as you did in school when you started learning math, we're going to start with a very basic math instructions, add and subtract. In the lab project, we had you create these 2 rungs of logic, one rung for add, one rung for subtract, and pay particular attention that source A is a variable, a pointer, named value 1, and the destination is also value 1. In this particular case, we are modifying the value of value 1 by adding 1 to itself. Value, whatever value is in here, which right now is 0, plus 1 will equal 1. This now will equal 1. This is the same tag. Same tags down here. So we're going to demonstrate the add and subtract instructions against one single pointer, one single register in memory. In the lab, with both switches off, I had you enable the add and watch the memory location of value 1, and then after a few seconds or so, disable add. I'm going to push input 0 push button, add enable. You see it's enabled, and you can see what the value is doing for source A. It's scan counting. That means that every single scan of this program that this rung condition out is true, it executes that add instruction and it adds 1 to itself. When I let go of the button, it stops. Sometimes people try to use the add and subtract instructions and they're expecting it to only increment or decrement by 1 when the rung goes true. And that statement by itself is correct. The problem is that for every single scan that the rung is true, it's going to execute it again. So the add and the subtract instructions both have true only execution. Right now the rung is false and it's not executing. A count up and count down instruction, which we've already covered, you could say they have a built-in one-shot. For every false to true transition of the rung, the count up and count down execute once, and they do not execute again, even if the rung is true, until it goes to false and then back to true. Next, I had you repeat that with the subtract. So I'm going to push in input 1, which is the subtract enable, and you can see what the value is doing. It's decrementing by 1 every scan. So you're basically looking at a reverse scan counter. Regardless, it's responding every single scan. Well, that's about as close as I can get to 0. Directly answering the first question in this lab section, what did the instructions do to value 1 as long as one of the switches was held on? The add instruction was a scan count up, and the subtract instruction was a scan count down. The next thing we did in the lab was add one-shot instructions. I'm going to do these in front of you in the online edit mode so you can see how simple it is. I created a tag, or we'll create a tag called one shot, but it's going to be a dent. And then after I've created it, I can't leave it on that instruction because that's a bit instruction and one shot is a dent. So I simply add the bit and that rung is done. Go down to this rung. We could go copy, instruction, click on sub enable, Control V, double click, backspace 1, and done. Finalize all edits. Now we have one shots. I'm going to clear this value, just type in 0. Now I'm going to push the add enable button. I'm holding it in, you can see that it's true, and you get one increment for each false to true transition. Same thing for subtract. Quite often I, in my logic, use the add instruction instead of count up, and I use subtract instead of count down. There's a lot of reasons for doing that that have evolved through many new product introductions, going all the way back to PLC2, PLC3, PLC4, very short-lived product, PLC5. Still one of the, still a high population of PLC5s out there. Then, of course, SLC 500, MicroLogix, then ControlLogix, CompactLogix. Through the years, there's been many reasons to use the add and subtract instead of count up and count down. But you have to always use a one-shot instruction with them if you want to use them as counters. To demonstrate the behavior with the one-shot, I had you clear the value in the register value 1, and then enable the add and watch the memory location. Toggled it up to 1, and then I had you do it 4 more times, or up to a value of 5. What is the value in memory location value 1? 5. Toggle the enable of the sub instruction on off 6 times. What is the value? -1. We could have used unique memory locations for each of these math instructions. However, we wanted to demonstrate both the nature of the math instructions, that they are executed each scan, that the rung is true, and that any math instructions can operate against any single memory location. It is very common to stack math instructions that execute against one single memory location in one single program scan. And we'll demonstrate this off and on in this volume. In the next step of the lab, we had you edit your logic to accumulate cartons, virtual cartons on virtual conveyors. This is a graphical illustration of 2 powered conveyors, 1 conveyor and 2 conveyor. Each conveyor has a photo eye at the entrance to detect cartons arriving and passing all the way on to each conveyor. The cartons arrive at one conveyor by way of a gravity conveyor, the rollers you see to the left. One conveyor is turned on, then they're pulled onto the conveyor and they pass through the optical path of 1 PE, and the same for 2 conveyor. If they're pulled onto 2 conveyor, they pass through the optical path of 2 PE. This is the logic in the form we had you edit yours to resemble. Occasionally you might notice slight differences in what I have on the screen compared to what you have in the manual. I try to make them look exactly the same. There are a few little points that really isn't going to matter, like the tag names. We use the same actual I/O addresses, but we may abbreviate something different. We may have something slightly different in the code. Nonetheless, this is the code that you have in your manual. Using input 0 and input 1 to simulate cartons passing photo I1 and photo I2. Toggle 5 cartons onto conveyor 1 and then toggle 6 cartons onto conveyor 2. Now keep in mind what we're doing here. remember the graphic that we showed you. So I'm going to press input 0, and that's in rung 0, local 1i data 0. I'm going to press it 5 times. 1, 2, 3, 4, 5. I didn't hold the button down long enough for you to see the instruction right here. This instruction change state. If I were to do that, I'll just put that back to 0. Notice that immediately I got an alarm, an odd alarm. So I'm going to toggle that back off because we don't want that on yet. Well, it's not going to let me toggle it off. I need to clear. And then push the reset button. Okay, so let's do this again. First instruction in rung 0. 1, 2, 3, 4, 5. Now I did it slow enough so you could see the screen change state. That's not necessary. Then I had you toggle in rung 1 the photo eye at the entrance of conveyor 2 6 times. Now I'm going to do it real fast, and you'll see the screen just doesn't respond. The graphic card in your laptop or your desktop computer and communications even over Ethernet. We're using Ethernet. It's just not going to update fast enough for you to always see it. 1, 2, 3, 4, 5, 6. I saw it come on once on the screen, but it definitely accumulated 6 onto conveyor 2. But look what we have on conveyor 1 now. We have a -1. So if you think about the graphic, that would literally be impossible to have 5 cartons arrive onto conveyor 1, travel down the length, and then have 6 travel on to conveyor 2. That can happen if somebody walks by and puts their hand in the photo eye, increments 1 more onto conveyor 2, and decrements 1 more off of conveyor 1 when there's really not any there. The only reason that we're doing this is to demonstrate the math instructions and how you might use them in a practical application. When we did this, we got a -1 here. We have a miscount. The question was, did the audit alarm come on? No, it didn't. Why didn't it? I mean, we did toggle 5 cartons into the system and transferred 6 onto conveyor 2. However, we created a negative value, and the way the math instructions work, if we add a -1 and a 6, we end up with an audit count of 5. And 5 is correct. We literally only have 5 cartons. However, we want to have an alarm if this situation happens. In other words, if there's a miscount, we don't want it to correct the miscount because that's not possible. The logic cannot correct a miscount because it cannot see the conveyor. And this is a miscount, but the auto alarm did not come on because we now show that there are 6 on conveyor 2, but there are not. There are only 5. We had 6 transitions, true, false, true, or false to true of photo eye 2. But we did not have 6 cartons travel on to conveyor 2. We only had 5. The other one was some other incidental breaking of the optical path that caused the miscount. So this logic didn't work because if you add a -1 and a 6, you end up with 5. And the audit count matches the production count. So the production count is the bona fide count in the system. Conveyor 2, though, says it has 6, which is a miscount. This -1, you can't have a -1 carton on conveyor 1, so we have to do something to prevent that. To prevent that possibility of having a negative value for the number of cartons on conveyor 1, to improve our situation, to reduce or eliminate having a negative count on conveyor 1, we're going to edit this rung. We're going to swap the add and subtract, so we add before we subtract. Then after the add instruction, we're going to put a greater than. that the accum conveyor 1 value has to be greater than 0. We'll change this to a 0. And as soon as I do that, I now have an audit alarm. We did have a miscount, but the miscount did not trigger the audit alarm because we created a negative number on conveyor 1. -1 plus 6 equals 5. So the production count did match the total number of cartons when you added the cartons on conveyor 1 and conveyor 2 added together. Now this logic functions. We added a comparison function to prevent decrementing conveyor 1 count below 0. But we also moved the subtraction operation after the add to allow the add, but preventing the subtraction if the conveyor is actually empty. Although we are not emphasizing applications, we do like to point out potential problems encountered in the real world and how to address them with logic. So this gives you a practical application for the add and subtract that really have nothing to do with higher math functions. This is simply management of product count on your conveyors. How could an object leave conveyor 1, pass through the photo eye onto conveyor 2 if conveyor 1 is empty? It cannot. Therefore, if the photo eye on conveyor 2 is blocked, incrementing conveyor 2 count and attempting to decrement the count on an empty conveyor 1, that is a problem. How can we edit our logic to address that? What can we do about it to avoid the problems that it might create? Or will our existing logic raise the alarm if this scenario occurs? Remember that we are discussing the math instructions and not developing a conveyor application. So don't get sidetracked by the weaknesses of this virtual application. Clear all counts and reset the alarm. So I'm going to reset. If I reset the alarm now, it won't. So I'm resetting it, but it's not going to reset it because the logic is going to continually declare an audit. So let's just set all of our counts to 0. Now we reset the alarm. We have empty conveyors. Increment 5 objects onto conveyor 1 and then 6 onto conveyor 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. You see, we instantly get an audit alarm. Why did we get the alarm? 5 counted into the system, and then 6 counted onto conveyor 2 with only 5 that could possibly have been on conveyor 1. This may seem sophomoric, that we're over analyzing the situation here. What else could we add to further eliminate miscounts? Visualizing your virtual conveyors, what else could we add to reduce the possibility of a miscount? Well, if you think about your conveyors, if cartons are moving through the photo eyes, then the conveyor belts must be moving. They must be running. So if we do not allow the add and subtract functions, the increment and decrement functions, unless the conveyors are running, then we've eliminated any problems caused when the conveyors aren't running by someone coming up and flagging the photo eye when the conveyors are off. So you see we've added conveyor 1 running as a permissive, a condition, into rung 0, and conveyor 1 and conveyor 2 running to increment or decrement conveyor 2. So we had to clear all counts, toggle PEs without the conveyor running. So I'm going to toggle photo eye 1. Somebody walked by, sticks their hand in the photo eye, does not count any on. Conveyor 2. So you see, if the conveyors aren't running, the counts are not affected. Toggle conveyor 2 running on. Toggle photo eye 2 on. Do the counts change? No. Conveyor 2 off and conveyor 1 on. Toggle this off. Toggle this on. Toggle photo I1. Do the counts change? Yes, they do. Which? Conveyor 1. With only conveyor 1 on, toggle photo I2. Do the counts change? No, they do not. So that's just a little brief introduction to the add and subtract math functions. The main things to remember is that if you only want them to execute to increment once or decrement once, you need to use a one-shot instruction. Otherwise, you end up with a scan counter.